we're going to pick up where we left off, and now we're looking at the laws of thermodynamics. There were originally 3 laws of thermodynamics, and there was this extra rule that we kind of knew about, but it had never been formally stated as a law, and it was too important to call it the 4th law. So rather than going back and renumbering the old laws, we just called that one the 0th law. So for starters, the 0th law of thermodynamics. It says when 2 objects are at different temperatures and are in contact, heat energy will flow to them until their temperatures equalize, or until they reach something called thermal equilibrium. The interesting thing here is they do not go until their heats equalize. You would think it would go until the heat energy here equalizes with the heat energy here, but that's not what happens. Instead, it's until the temperature here equalizes with the temperature here. The random motions of these particles transfer to these particles and till they reach some average random motion. At that point, their temperatures are different, but their heat energies are not. It turns out that heat loss is always equal to heat gain, so the amount of heat energy that one part loses is always equal to the amount of heat another one gains. And heat energy always flows from hot to cold, from stuff that has energy to stuff that doesn't have energy. Cold doesn't flow, cold doesn't transfer. Cold is just a lack of heat energy. And I always joke that when your mom complains that you've left the door open in the winter and you're letting all the cold in, you can correct her and say, "No, I'm letting the heat out." You'll probably get in trouble for being a smartass, but you'll be at least scientifically correct. Of course, the reverse process is true in the summer when she complains that you're letting all the cold air out. You can say, "No, I'm letting the heat in," with the air and conditioning, and you can apply it to fridges and whatnot else. Don't be rude to your moms, but the correct heat transfer is from things that have heat energy hot to things that don't have heat energy that are cold. Newton actually studied this, and he came up with a law. This is our final law of Newton that we'll talk about this year. Yeah, that's true no matter where we're at in the year. This is the final law of Newton that we'll talk about this year. Even though he dabbled in a lot of other areas of physics, there's 4 laws named after him in motion and mechanics. We have the 3 laws of motion and the universal law of gravitation. Newton's law of cooling is the last law that we have that's actually named after him, even though he does have some optics laws and some other rules here and there. But basically, he says the rate of cooling of an object is proportional to the temperature difference between the object and its surrounding environment. Basically, if you have an object at a certain temperature, it's going to cool, and is going to, the greater the temperature difference is, the quicker it's going to cool off, the quicker it's going to transfer its heat energy. There are some other factors involved, and it actually takes an area of calculus called differential equations to be able to calculate all this out. Having said that, experimentally, it's not too bad to come up with and such. Turns out there's 2 interesting things here. One is an application. This is used in forensics a lot, and I'll explain that one in class. The other one is it turns out that the object that's cooling will never actually reach equilibrium with the room. No, that's not right. Crap. 2 things I want you to think about here. One, there are some applications, one of which is in forensics, and I'll talk about that in class. The other one is it turns out that the object that is cooling will never actually reach room temperature as it cools, and I want you to think about why that is. That is, we have a hot object and it will cool down, it will cool down, and it will cool down, but it will never actually reach room temperature. If you carry this graph out, it actually goes out to infinity, and it will never reach the room's temperature. And I want you to think about why that is. Anyway, the first law of thermodynamics says that whenever heat's added to a system, it transforms into an equal amount of some other form of energy. And so, really, the first law of thermodynamics is an early statement of the law of conservation of energy, but basically we add heat to a system. Some of that goes internal into the system and becomes just heat in the system, and some of that can go towards the system doing work. And so we have a formula that Q equals the change in internal energy, delta U, plus work done, W. But basically, energy in equals energy out. It's just that sometimes that energy gets stored inside the system, and sometimes that energy gets used by the system to do some useful work. And we'll get into that when we talk about heat engines. The second law of thermodynamics really says that heat will never on its own flow from cold to hot. That you'll never have a transfer of heat energy from a cold substance to a hot substance. And the second law of thermodynamics is often misquoted and is often abused, but it simply says that heat never on its own flows backwards. There are some interesting implications from this. It turns out then that because of this, things are constantly getting more randomized, and because of that, the order of the universe is decreasing. The disorder of the universe is increasing, and that's something called entropy, which is the measure of the disorder of a system. And because of that, this law is sometimes called the law of entropy. But it does not mean that systems cannot become more ordered, and it does not mean that we can't have that heat transfer happen. It just doesn't happen on its own. We have to input energy. And so, for example, you clean your room one day and you leave it sit there and you never work on it again, it will naturally become disorderly and unclean. It'd be great if it just spontaneously cleaned itself, but that's not what's going to happen. The universe says it's spontaneously going to get more and more messy. Even if you shut it off and never do anything with it, if nothing else, dust is going to settle and things are going to end up slightly more disordered than they were, even if you don't mess with it. But if you're using your room, of course, it's going to get incredibly messy. Now, you can make your room orderly again, even if you don't want to, by putting a little bit of energy into the system and doing a little bit of work and doing that. But it turns out the second law of thermodynamics tells us there's a consequence. Although that system can become more ordered because of you input energy into it, the surrounding systems, that is your body and just the air and the rest of the universe, actually becomes more disordered. That when you order this, something else becomes even more disorderly somewhere else. And lastly, the third law of thermodynamics that says that as temperature approaches absolute zero, entropy or disorder approaches a minimum. And it turns out there's a consequence of this that actually says that absolute zero is not actually obtainable. That is, even though we know that there's this absolute minimum temperature, we cannot actually get there. We can get really close. In the lab right now, we've been down to within 1/billionth, that's with a B, billionth of a degree of absolute zero. We've gotten in incredibly close. Also, it's frequently misstated that absolute zero is where all motion of particles stops, and that's not true. The vibrations and the rotations of particles will stop, but the motions within the particle, the electrons moving around and the vibrations in the nucleus, don't go away. And so we don't get all motion stopping, but we get most motion, all the external motion, if you will, stopping on atoms, if we could get down to absolute zero. And we've gotten really close. The analogy I like to give, though this is a little bit misleading, is that to cool something down, you have to put it in a colder environment. So to cool something down to the absolute minimum temperature of the universe, you have to put in something even colder. And of course, that's not possible. We can't put it into something colder than the coldest temperature possible. And so we can't actually get to absolute zero through normal means. Now, it turns out there are some other means by which we can approach it without having to have a colder surrounding by actually sapping energy out of the system. And it's really interesting because we usually use lasers, and we usually think of lasers as heating things. But if you line things up just right, you can actually use a laser to cool it down instead of heat it up. And we've actually gotten really cold, and some weird things happen down at the atomic level. But that's a chemistry topic instead. Anyway, absolute zero, as I've mentioned already, is the lowest we can go, and there's the actual temperature values for the different common temperature scales. And that finishes up the laws of thermodynamics, and next time we'll get into applications. If you have any questions, be sure to jot them down and bring them with you to class.